you learned about back library, you learned about yak library. Now a small topic that comes inside this is, how do you know how many clones do we need? எவ்வளோ clones இருக்கணும் ஒரு genome size கிடைச்சா how many clones should we make? That is how that we can determine the number of clones. We can determine by determination of the library size. அதுக்கு ஒரு formula இருக்கு, very simple formula. You just have to put it in the calculator and find it out. Okay, so the larger the fragments that the clone that are cloned in a particular vector, the smaller the overall size of the library. Correct? Yeah. If you break it down into very, very small pieces, you will have many pieces. So that many clones have to be made of that genomic DNA. That many host DNA has to, you need so many clones for that. But if you break down into smaller pieces, that is not smaller pieces, if you have fewer cuts, okay. For example, I have my pen over here. You cut it over here, here, like this. You chop it over multiple sides. You will have small pieces, say 10 small pieces. That means you will need 10 clones, right? To get the copies of each gene, you will need 10 clones. But if you use a restriction enzyme and cut it over here, say over one over here and one over here, you have 1, 2, 3 pieces. So to make a genomic library of this, you will need only 3 clones. Minimum 3 clones. One will copy this one will copy this one will copy this portion. So you understand, that is what they meant. The larger the fragments that are cloned in a particular vector, the smaller the overall size of the library. The initial case, you had 10 fragments, you needed 10 clones in the library. So that's a bigger size. When you have 3, you need only 3 clones, which will multiply the same genomic DNA of interest, and your genomic library will be smaller. So to find out what is the minimum number of clones needed, you have a formula which is n is equal to natural log of 1 minus p divided by natural log of 1 minus f. Now what is this? N is the minimum number of required clones. Namukku ethana number venum, clones evlo irukku, that is the minimum number. That is what we have to find out. P is the probability of recovering a desired DNA sequence. Usually everywhere, if it is not mentioned anywhere, P is always 0.99. 99% probability that you will get your desired gene. Okay, usually it is over there. So if it is in a question, it is not mentioned, you can take it as 0.99 everywhere. This P will be 0.99. Then F is the fraction of genome present in each clone. Fraction of genome present in each clone na enna? This is your whole genome. Idukku oru size irukku. For example, its size is 10 or its size is 100. Okay, you break it down at say 5 places. In the big 100 kb genome, you've broken down into 5 fragments. So each genome etna size irukkum? Let me. Okay, so you have your genomic DNA. You have cut it at 5 places. So each piece will be 20 kb. I hope it is clear to everyone, right? So what is this fraction? Thank you, Soumya, for answering. Thank you. So how do we calculate the fraction? Fraction is nothing but this size, that is that 20 kb size divided by the whole size, 100 kb. So 20 by 100. That will give you your fraction. 20 by 100 will be the F over here. Okay, so fraction of genome present in each clone. That is your fraction. So now we'll be seeing an example. Okay. Example is, you have the human genome. Suppose its size is 3.2 into 10 raised to 6 kilo base pairs. Okay. Kilo means again it is 10 raised to 3. So this is actually 3.2 into 10 raised to 9 base pairs. Now, if lambda vector can accommodate 70 kb inserts, that means this vector la ungalku 17 kb size da poda mudiyum. That means evlo fragments irukum, your thing will be 17 by fraction will be 17 kb by 3.2 into 10 raised to 6 kb. So what you will do, what is the minimum number of clones that you need to produce? You can put it in the formula. N is equal to log of 1 minus, as I told you, probability P is majority of the time it is 0.99. Okay, 99%, divided by log of 1 minus your insert size. This, what they have done is they have made it into BP, that kilo base pairs, no, into 10 raised to 3 irukalla, appo 1.7 pota, it will be 1.7 into 10 raised to 4 BP base pairs, divided by your whole genome. This thing divided by this thing is the fraction, right? So 3.2 into 10 raised to 9. 9 eppadi vandhathu? 6 plus kilokku 3. 6 plus 3, 9. So 3.2 into 10 raised to 9 base pair genome. Okay. Make sure that both these units are correct. If you are putting this in base pair, this should be also in base pair. If this is in kilo base pair, you put it in kilo base pair. Okay. You could have simply done it like 17 kb divided by 3.2 into 10 raised to 6 also. It will give the same answer. But the calculate பண்ணும்போது you will get 8.66 into 10 raised to 5 is the minimum number of clones. That means in the genome, if your human genome is there and you're using a lambda vector, அதுக்குள்ள 17 kb size தான் போட முடியும். அப்போ எத்தனை fragments இருக்கணும்? These many. 8.66 into 10 raised to 5 fragments பண்ணணும். Minimum number of cloning அவ்வளோ பண்ணணும். Okay, so minimum number of these clones will be 8.66 into 10 raised to 5. Okay, so huge. 10 raised to 5 எவ்வளோ zero இருக்கும், right? So usually what researchers do is they will make genomic library 2 to 2.5 times the size required. But this is the minimum size required. What people will do is they will make multiple copies and 2 to 2.5 times extra panni vikkum, so that there is a surety that all the pieces of genomes are pakka there. Okay. Now I have a question for you all. So you know our formula, right? This is our formula. N is equal to ln 1 minus p divided by ln 1 minus f. If you can see this question, can anyone tell me, or else what I'll do is I'll show you how we will solve this. The size of mouse genome is 5.6 into 10 raised to 6 kilo base pairs, mouse genome. And average clone fragment size is 40 kb. How many minimum number of clones are required to represent a particular sequence? What I'm going to do over here is, I'm going to open up a calculator. First time I'll show you, I'm going to calculate this in front of you. Okay. So n, that is the number of size clones that we need to make, is equal to log of, where is my log over here? Natural log of 1 minus p. So p is not, probability is not mentioned here. So I will take it as 0.99, 0.99, 0.99. Okay. Divided by, I'll put in the bracket, divided by, again, log of 1 minus your fraction f. F is nothing but, this is your fragment size that can be cloned, 40 kb. And this is your whole genome, 5.6 into 10 raised to 6 kb. Both of them are in kb, so I'll put it as like that itself. Okay. 6,44,721. So that is what is the answer we have over here also. 6.4 into 10 raised to 5 number of clones. A calculator over here. So this is the answer we have got. So I've used natural log. Very simply, I have put the formula in front of you. Okay. Next, I have put a question for you over here. In question number 1, that is here, what if the probability is 95%? So instead of 0.99, what will you put? You'll put 0.95 and you'll get this answer. So you can calculate it and see. When I share this slide with you, you can calculate and see if you're getting the answer. So sometimes they will give all the other information and they will ask you to find the probability. Sometimes they will give the number of clones and they will ask you to find the genome size. So put it anywhere in the formula and get the result. Okay.